Hi, today I would like to talk about easier machine learning and share some thoughts from the Scikit-Learn project. So, Scikit-Learn, we started more than 10 years ago, and honestly, we were really a bunch of nerds back then. And it seems that these days we've become an industry standard. We have almost a million, monthly users. But the thing is, back then we were not aiming for the enterprise. We were really aiming for ourselves. So basically, scientists, students, hobbyists. And we've reached a situation where we're used by a huge amount of people in a very large setting. And if you hear the news, it's all about the data. However, our goal was never to reach the mighty, but more to reach the many. And if you look at the average, the typical data set that people work with, the size is rather in the gigabyte, in a dozen of gigabytes, rather than in multi-petabyte settings. So this is actually a good news because this was the type of data that we had, and it seems that it's the type of data that many people have. Another interesting data point is that this amount of data is not increasing with time. Basically, the typical data set that typical data scientists work with has a fairly constant size. So once again, it seems that our usage is typical of many usages. But if we go beyond this, we hear a lot in the news about applications of data science or machine learning or artificial intelligence to very, very large data sets on very, very difficult problems. However, if we step back and we think about the impact that machine learning or artificial intelligence can have on society, well, there is one is that it can concentrate wealth in the hand of a few mighty actors and create more inequalities in wealth and power. But there is another possible consequence, is that it can also improve medicine, education, public policy, and open new doors to little people. And this is personally what I'm interested about. And to achieve these goals, we need to enable machine learning without very large resources, infinite data, and Ivy League education. And this is basically what I'm excited about. Now, if we look at what challenges people have in data science, and this is a survey that was done by Kaggle on their public, so people mostly from private companies, and they asked what are the most important challenges that people face in their day-to-day data science practice. And the number one challenge that comes up is dirty data. Whatever that may mean, we'll have to think about this. And the second challenge is the lack of data science talent. And only after, people complain about other resources like money. So if we want to lower the bar, we need to help integration of non-curated data. And we need to enable the human in data science. And we need to work on computational efficiency. So if we think about what we've done and what we're working on and to enable easier machine learning, I first want to discuss things we've done in the past, building Scikit-Learn, and that is building machine learning toolkit for all. Then I want to discuss ongoing progress, which is to make it scale better and compute faster, and then give you an idea of some research work that we're working on today, which is how to integrate non-curated data better. So to start with the Scikit-Learn story, our goal was really to build a machine learning toolkit for everybody. And for this, the first thing we did was that we embraced the Python stack, which back then wasn't as popular as it is today. The reason we chose Python is because it's interactive and easy, but also because it's general purpose. So it can be mixed with other tools that are not pure machine learning, such as web stack, text processing, image processing, you name it. What was crucial for our success was that Python was built from the beginning to be embedded. And this conditioned the choice of a very simple virtual machine. So it doesn't have fancy and powerful things such as transactional memory, and rather it has very simple tools such as reference counting, garbage collection. This means that it is very easy to couple the Python virtual machine with external programs. The other thing that we embraced was Numpy, and we embraced it for the numerical operations that it gives us. But really, the way we need to think about Numpy is that it's a continuous memory model. So it's some form of float star, some form of C pointer, and an abstraction on top of this. And this is extremely useful because it allows us to couple to other libraries. And so these two features are crucial because they enable bridging across languages. So typically we can reuse code in C, such as laypack, and they also enable Python, which is some form of a high-level compiler from a Python-like syntax to low-level, such as C. And we've been using this hugely in Scikit-Learn. Next, because our goal was to enable people, we focused a lot on usability. And for this, we put a lot of effort on API design. The principle behind our API is the principle of gray box. The idea being that all models are interchangeable, but they're still inspectable. You can still, to a certain point, open them and look at them. We also invest hugely on documentation and example. There's so many problems that are better solved by explaining something rather than coding more complex models. And the way we do it is that good documentation is required to add a feature. We guide our API design by crafting easily understandable examples. And our goal when we write Scikit-Learn documentation is an example is to teach statistical learning and not to teach code. Ideally, people shouldn't worry about syntax. They should worry about the data science problem they're working on. When we integrate code, when we integrate a statistical model, a solver, when we make choices of hyperparameters, each time we make those choices, we choose the option that does not require tinkering from the user. And this is actually a very difficult problem. And we do this via a lot of use case-driven empirical testing. Finally, the secret weapon of Scikit-Learn has been the community. From the start, our decision-making and our development has been distributed across many countries, many continents. This gave us manpower. We have typically 30 to 40 monthly contributors, and they're not the same people every month. So this brings a lot of different people to work on the project, but it also brings a lot of diversity, which is extremely interesting because this diversity helps us have the right focus. People will come, fix, and improve what's important to them. So it is fair to say that open source has won. This is a successful open source model. However, it needs sustainability and it needs continuous investment. And more recently, we've turned to private partners. We've built a foundation where we have partners who are mentors, and they help us pay core contributors who work on the project and support the wider community. Now, Scikit-Learn is working very well. And the question is, how do we enable it to tackle bigger and problems on smaller computers? So we've been working on improving the efficiency of Scikit-Learn on a single core up to many computers. And I'd like to give you a few hints of the things that we're doing. Our first focus is on better algorithms, because better algorithms allow to make better use of the same hardware. So take an example of the principal component analysis. Principal component analysis reduces the data by finding the directions of maximum variance. Its computational cost scales as n, one direction of the matrix, P, the other direction of the matrix, times the minimum NP. So it's quadratic in one of the two dimensions. So it can become costly. And there's one way of decreasing this cost, which is to use randomized algorithms. The idea of a randomized algorithm is that it will benefit from the redundancy of the data to take shortcuts. And randomized PCA, if I can give simplified intuitions, the way it works is that it takes a random fraction of the data. It does a small PCA on that random fraction, and that small PCA is much less costly because of the quadratic cost. And then it does this many times, not too many, maybe a dozen, and it aggregates the results via PCA across the results. And so this is now the default in Scikit-Learn PCA, and we embedded heuristics that turn this feature on and off depending on whether it's likely to be successful. This is with the default solver, which is auto. And in our experience, it typically gives up to 10x speed up on the same hardware. Another common use case, another common model is logistic regression. So logistic regression is a linear regression. And so it's a cost that needs to be minimized, and it's traditionally minimized by a gradient descent on a measure of the error to minimize this error. And when you have a very large number of samples, then the error or its gradients are costly to compute because they're the sum on all these samples. So you can take the full gradient, so summing on all the samples, and you get a nice convergence. You can take a small number of samples to compute the gradient, and you can change the small number of samples. And if you do this, you get what's known as a stochastic gradient descent, which I've displayed here. However, the problem with stochastic gradient descent is that it's quite finicky and may not converge well. And so what you can do is that you can combine this idea of subsampling the gradient with the idea of a noise reduction, which is to take an average, a clever average with the past. And for this, there's an algorithm that's known as SAGA, and it gives you the best of both worlds because it's not finicky, does not require you to choose well a learning rate, and it's much faster because it can exploit the redundancy in the data. So that's an example of an algorithmic improvement. And finally, if we look at gradient boosted trees, the trick here is that we're going to fit those trees on sufficient summary. And the idea of gradient boosted trees is that they're a succession of decision trees. So decision trees are basically partitions of the feature space. And this succession that is built one after the other, and they enrich each other and they become finer and finer. And so one thing that we did recently is that we borrowed a technique that's used in XGBoost and LightGBM, which is to compute histograms of the features and to bin the data on those histograms. And so basically we're taking the data set and we're computing binned a feature from these, and then we're computing the partitions of the data on those binned features. And this gives orders of magnitude speed up when the data is very large. And it's implemented in a new model, that came out last year, that is called HIST gradient boosting regressor or HIST gradient boosting classifier. So there is a common thread to those algorithmic improvement is the idea that we're going to fit on several subsamples or chunk, and then we're going to aggregate or do variance reduction or fit on summary statistics. So these are statistical tricks to compute, to solve faster statistical estimation problems. Now, once we've done this, maybe we'll want to use more cores, use bigger hardware, in which case we'll be looking at parallel computing. And the problem with data processing and parallel computing is that you need computing schemes that limit data transfer. And there's typically two of these schemes. One is the data parallelism, which assumes that you can divide your operation on different blocks of data and execute it in parallel. And the other idea is model parallelism. You're going to fit many different models on the same data, and you can do this, for instance, for model selection. Now, in real-life machine learning, you have a combination of those patterns and many other patterns. In Scikit-Learn, we use different implementations for the different patterns, though there are multiple patterns. For the inner loop, we need extremely fast parallel computing, and for this, we use operating system level threads. Or OpenMP, using the implementation of OpenMP from the compiler with which the library was built. However, the challenge is that we're combining many different libraries because we're using combination of SciPy. We are used in settings with various linear algebra packages. We might be used with other libraries. And as a consequence, there is a competition of all those libraries that live in the same process. And the danger here is to have oversubscription. On the other end of the spectrum, we have large-scale parallelism, in which case we need to work across multiple Python virtual machines or across computers. And there the challenge is transfer of data and synchronization across those workers. So the real life is we have a combination of all this, and it's a merry mess. We often have oversubscription, inefficient transfers. The core problem behind this is that of scheduling. However, as a library, we're used in bigger settings, so we do not want to implement a scheduler. Rather, what we need is a simple API that enables us to focus on algorithmics, but to delegate the scheduling to an environment. The idea being that Scikit-Learn is a library, it doesn't own the main. And for this, we've been relying on Joblib. Joblib is a very simple pattern that enables parallel for loops. However, it comes in with many different tricks. It, for instance, can manage a pool of Python virtual machines. It can do lazy loop consumption to limit memory usage, or auto-batching to lower overhead. It can limit the number of threads in a sub-process. More interestingly, Joblib can delegate its work to backends. And so it can delegate its work to a complex scheduler such as Dusk. And to me, this is an exciting alley to have Scikit-Learn work in larger settings. We've also been working upstream, improving the Python virtual machine, improving pickling, which is crucial when you need to transfer objects from one machine to another one, improving predictors, the idea being that you can persist Scikit-Learn in language agnostic representation that can then be used in production in other virtual machines, such as with a C++ virtual machine, and that's very useful for deployment to production. So we're trying to couple in a larger ecosystem. So for scaling, algorithmic improvement is our top priority. However, we are working on coupling to external infrastructure to scale out. I'd like to touch a few words before the end on the integration of non-curated data. And the idea being that dirty data is a central problem, and it comes from merging different data sources or input errors. And one of the challenges that we have here is that there are a bit two communities that work here. One is the statistic communities that works with numbers and arrays. The other one is the data engineering community that works with strings and databases. And so we need to sit in the middle of those two. So this is illustrated by the fact that in most machine learning papers, the data is assumed to live in a vector space. It's a matrix. However, in real life, the data is typically a dirty table that might have missing values or non-curated, non-normalized entries. So what can we do about this? Missing values, traditionally what you do is that you replace missing values by plausible values. This is known as imputation, and Scikit-Learn can do it. However, what we've shown in a recent paper is that imputation can be a bad idea because the target that you're trying to predict may depend on missingness. So you need to add a missing indicator, or for powerful learners, a simple imputation, like constant imputation, actually works better. But the best option is to use the support of missing values that comes in our latest Hist gradient boosting classifier. Now, when you have dirty categories, One of the tricks that we can use is that we can use their string representations, and we can encode them with their string representations. So instead of the traditional view, which is to do data cleaning using feature engineering, what we'll do is that we will represent the data using string similarities. And this can be done using the Dirty Cat library. The problem with this is that it might not scale very well because we might have an explosion of different strings. And so what we can do is that we can do a substring model that actually finds recurrent substrings and encodes on these recurrent substrings. So what we've learned working with dirty data is that we should do more learning and less cleaning. And for this, we need representations and models that can ingest non-curated data. This is all I have for today. Thank you.